see if we can make it through the part 3 of firing. All right, common kiln problems that contribute to defects. It's not always the product. Accurate temperature measurements, large temperature variations, obviously through the package, uneven airflows, which can also lead to the large temperature variations, but also, again, what John, I think he's talked about on hardening of materials, of brick, and getting the oxygen to react with the materials is the big thing. If you actually break a brick apart and it's got a black core to it, what's the black?
Iron.
You would think, but typically not. What's happening is the black is actually the organic there, the carbon there, but it has a higher affinity for the oxygen, so it actually strips oxygen off of your iron and turns your iron from red to black. So it takes it from Fe2O3 to Fe3O4, which sounds kind of odd in that it going from O3 to O4, that's another oxygen, but it's per how many irons you have there. So Fe2O3 actually is more oxygenated than Fe3O4. Okay. Backdrafting can also lead to issues if it's not done correctly. Condition of kiln, the refractories, the offtakes, the seals, the dams, if you have air leaks, those can all affect what the profile of not just the overall car, but individual areas of the car, which will give you a lot of variation in the cars. Condition of equipment, the burners, the controls, how well they're actually controlling the mixture, and whether some parts you could be reducing around the product, or the excess air is off and you're cooling different areas. Again, you guys have kiln experience to where producing a cool flame, you guys are familiar with that, to where you're putting in oxygen, and if your burner supports a lot of excess air, on our Swindell kiln we can go to like 40,000% excess air, and we keep the oxygen going steady and we just vary the gas, and I can get the flame temperature with 4 burners on this periodic kiln that's probably 10 by 6 feet. With 4 burners on, I can hold temperature at 200 degrees inside the kiln, because there's just so much air going in it that is basically taking the BTU and absorbing it, that it's keeping the temperature from raising. So you're basically cooling the flame. And also varying load size shapes, that if you guys know, if you're pushing mods and you switch over to Kings, you're going to need to make some changes on the kilns, because your setting pattern is going to be different, the actual pounds of material there are going to be different, and those are the things you have to compensate, and if you don't, the product will let you know. Common product problems that contribute to defects. Change in quality of raw materials, obviously, which is what we've been reviewing earlier with John, to where just looking at what you're digging out of the mine and putting into the product. Change in particle size, again, it's affecting how the brick is put together, how reactive it is, and how it's going to fire. Poor control of additives, to where if your additive A feeder is got a big flopping mess on it and it's spitting out every now and then you could end up with all sorts of deviations in your product. Poor blending, grinding, screening. Review of common firing defects. You need to look at kiln solutions, but you also need to look at potential product solutions, to where to say, okay, which one of these could it be coming from? And when you do a review, you need to keep the whole system in mind and not just typically run. Usually, I think the standard procedure is the kilnmen say it's the raw material problem, and the raw material guys say it's the kiln's problem, and it's not our fault. Is that still the standard process? Okay, just making sure. I've been out of the industry for a while, so I just wanted to make sure I still...
In your experience, what's the more common?
All over the place.
Really?
All over the place. What you need to add, I guess the big thing, one of the things that I try to promote in the businesses that I've worked in is the business is running great, that's when you need to do the most work. Find out where everything is setting, what everything measures, go through all your burners, take all the mixture settings off of it, take all your temperature readings, and monitor the bejesus out of it. And then that way, when something starts to go off, you look at the picture now and say, what was it then? It's the same picture on the kilns. I don't think it's the kiln unless the product is, we've actually changed product line, like I said, the brick size or something, but that's going further upstream. So it's like, okay, I'm pretty confident it's not the kilns because we're running mods and it's roughly the same settings and the same performance as what we had before. So there's something material-wise I'm going to go look at. If you go through and you compare them and it's like, well, why are all of Hot Zone 4 burners so off the, well, we did that a month ago because we didn't think.
Pressure outside.
Yeah. There was a squirrel that ran across the control panel, and we're pretty sure that he chewed on some of the wiring, so we had to rewire it. But I think the biggest thing is to go through, like I said, I wholeheartedly promote, if your plant is running beautiful, go balls to the wall and find out everything you can about your process at this point. Go through and record as much as you can, because that's what gives you the big picture and saying, okay, if something goes out, we've got something to compare it back to. If you wait till you have a problem, you're just guessing. You don't know. You can kind of, yeah, there's nothing to compare it to say, okay, we believe this has gone out, but if you had numbers to actually compare it to, that'd make life probably a whole lot simpler. Instance of a firing crack in a high kaolin brick. Firing crack in a face crack in the red brick. What you're looking at, and again, you guys have known this from experience, is you've got to get heat to the center of the package. You have to get heat to everything, and the ideal thing is to get heat around everything at the same time, at the same rate, and everything will be happy. If you could send one brick through at a time through your kiln, you'd probably have 100% yield. Wouldn't have a job for very long, but you'd have 100% yield. And the whole idea is trying to get it, usually when you start forming cracks, it's because you have something that is producing a differential, something that is producing a difference across the product. So if it's in the firing, you're going through and possibly shrinking one part of it before shrinking the other, and it's trying to catch up and it's putting stress on it. Typically, when you start firing a brick, you're going to put the outside in tension, the inside in compression, because you think when you fire something, you're shrinking it, so you're only shrinking the outside shell of it. So if this were a paver, you would be putting even more forces on it, because these little guys are helping you out with the mods and the queens and everything else that your kings that you're making, is that it's shortening the distance that the heat has to get to the center of the product when you're firing it, whereas if it was a solid paver, you're trying to get the center of this paver to be the same temperature as the outside. And that's the reason why you have to change your firing profiles. So that's something to think about when you're seeing cracks. Look at where they're occurring. Look at where they're occurring in the hack. Are they only occurring at the bottom of the car over here? Are they occurring at the top outside corner? Where are these things happening at, and what is the distribution? One of the things that we can look at too, that we have what's STATGA, it's thermal gravimetric analysis, and what it does is it looks at temperature change, weight change per temperature. So when you see this thing, it's like maybe the size of a racer is our little crucibles that we put material in, and it has a super sensitive balance on it. And we put a control sample and your sample on there, and then look at the weight changes. And what that can tell us is it will give us peaks to where we can look at what the water change in is a big thing. That can anybody identify what these peaks are from what John's gone through? Question and answer time. Part of the test. So we go through and we lose the first water. Where do we think this water is coming from?
That's the forming, then it's the core, and then it's the crystalline.
You've got the pore water. That's usually the easiest to get out. That's the stuff, the excess water that's sitting in the pores of the product, and that's what you're removing.
Mechanical
Then you've got the mechanical water, the interstitial water, the stuff that's in between the particles that allows the slippage when you're doing the plastic flow. And then the final one, when you're getting up 500, 600, 700 degrees, that's the chemically combined stuff. That's the stuff that's part of the, well, not necessarily the crystal, but part of the mineral, that you're actually breaking the bonds of that water and pulling them out. And again, this is just looking at the different materials for this particular one. There was also a hydrogen chloride peak as well for this particular material that was being analyzed. Face cracks. What are the solutions? So basically you need to know your materials, know your firing curve, strength of the body, whether to avoid poor mixing, better recirculation, opening the setting pattern, maximize core area, and then slowing the schedule. But again, you've got a schedule, a production rate that you're trying to meet. So you have to really understand, and it goes back to, again, all this stuff. When it's running good, gather as much information as you can, because when you do change something, you need to know what you changed and what impact it can have on all the other performances that are going on and that can lead to issues with your product. Okay, coring problems. Yep, this is what we were just talking about. So again, if you see coring, chances are it's because there was an organic in it. Now, there's a couple of different issues that you can run into when you do have high carbon or organics in the material. One is the coring, which from a strength standpoint doesn't really affect the brick at all. It's just a different color. It's a different state of the iron oxide. But the customer sees it and, ooh, our brick is underfired or ruined, they're not going to perform correctly. So this is giving some ideas of, again, looking at the thermal gravimetric of seeing the peaks that you'd form from all the organics as they tried to burn off at all the different temperatures. And where this can play a major factor is if you're, depending on your firing schedule, if you seal over the outside too quickly, you don't have time for all of that to get out of there, and when you heat up gas, what does it do? If it doesn't have a way to get out of the balloon, what does your brick do? This is looking at varying the firing rate to actually show that if you give it time for the oxygen to get in there, you can go through and get rid of the coring. But sometimes you don't have enough time or wiggle room in your schedule to do that. Coring and bloating are related to both indicate improper oxidation in the preheat. Black core forms residual carbon in the body, reduces the iron from Fe2O3 to Fe3O4. Bloating is an example or an extreme form of coring. And basically, again, you're sealing over the surface, and the gas doesn't have anywhere to go, and it just keeps expanding, and it just moves the material and turns it into a balloon. No one here has been to the short course at Clemson yet. We have you have, that's right, I remember. You remember the football? Yeah. Yeah, we have a brick that was turned into a football. Yeah. We had basically, I think it was somebody that Jim Fredericks at the center was talking to, and that particular person said, you know, there's our brick is so stable, there's no way to hurt it. And yeah, that's getting close to what the football is. But Jim just kind of smiled and, okay. And that's where the football came from. No, you can't hurt our brick. It's impossible. If you fire it fast enough, you will hurt it. So the whole idea is you're trying to produce a firing schedule that gives time for everything to happen. You've got to get the water out. You've got to get the organics out. You've got to get the thing to densify. You've got to get the pore structure. You want to keep the differential shrinkage to a minimum that isn't going to put stress and cause cracks in your brick. So everything that you're doing right now, you're actually doing a lot to get that brick out to be the right color, the right porosity, the right mechanical behavior. And if things start to wander, this is some of how it presents itself. Improving carbon burnout. Kiln design and operation increase the amount of available oxygen, and that's where we talked about going excess air on the burners. Open setting for getting good flow around the brick so the center of your package isn't a dramatically different color or even have different hardening properties from the outside of the package. Optimize the burnout schedule so that you may find that either from trial and error or sending us samples that, okay, there's a certain temperature range that you need to go slow through to allow this to happen, and you may be able to just adjust your kiln schedule to say, okay, we're going to come up from here to here. It doesn't matter as much, so we can come up a little quicker, but then we can soak a little bit longer at this temperature range before we head for the hills and fire the product. Body, look at the raw material selection. If the organics aren't there to begin with, then you don't have to burn them out, or as much organics. So that's one thing. Increasing permeability, putting sand additions in. Again, the sand will burn out and leave pathways for things to get out of the brick. However, you just put more carbon to burn out as well. So, and you're impacting your porosity that you'll have to address during firing. And then also looking at oxidizers, additions of chemistries that you can put in that the bond with the oxygen of that chemistry is such that it's weaker than everything around it. So when you fire it, it tends to evolve oxygen, which then reacts with the iron and changes the color of the iron. So this was looking at one such oxidizer to where we were looking at manganese oxide, and basically from doing additions of 0.5%, 1%, 2%, you can see that you're basically under the same firing schedule. You're reacting out. You're giving enough oxygen to take care of the harding. Now, what's the problem with doing that as well? Cost. But also, if this were a buff brick, oh, you betcha. So there's, again, you need to know your product line and weigh everything to say, okay, where we're at right now, what is the best courses to take a look at to try, and that, again, we can help with that to some extent. Coring example for red body shale. We've got a red body that has a tendency to have coring. The material had a relatively high carbon, and to improve firing curve and remove the heart, that the total carbon, organic, and again, we can do this analysis at the lab to find out what state these materials are in and how mobile are they going to be. And then doing lab trials, we looked at just doing no soak, 6 hour at 1200, 6 hour at 14, 15, and you can see as we got up to the higher temperatures, the reaction rate increased as well.
So 1600 sealed over and you can't get it out anyway.
It depends on your product. On this particular one, it was probably starting to seal over, but again, it depends on what materials you're using out of the mine, to where all of that's going to affect the temperature range at which because the more sodium you have in it, the more potassium you have in it, chemistry-wise, those all act as fluxes and actually lower the temperature of forming glasses. So depending on what the chemistry is, it will give you differences on when it actually starts to glass, when it densifies, when it does what it does. If everybody's material was the same, we'd be in the plastic industry. Oops. Yep. Okay. All right, so cooling cracks. This is the wonderful graph again that John was showing you earlier. But basically the takeaway is that quartz changes when you're heating it. And it will always change when you're heating it, when you're reheating it, whatever you're doing with it. So it's something to keep in mind. Again, 1066F is the scary zone. And if you believe that you are running into an issue, again, you can send us a sample. We can go through and put it either on our dilatometer or our XRF and go through and look and see what type of quartz is in there to find out, is that really a potential, and how much is there, how much size change is really going on, what's happening with the material. Again, depending on the size of the quartz, will put strain on the structure around it as well, and will cause, even the quartz itself will cause fracturing, internal fracturing. Dilatometry curve. Dilatometer looks at size change per temperature. So basically it has a little stick, spring-loaded stick that's up against the part, a little 1-inch stick of your material, and as you heat it up, it has a super sensitive micrometer on the end of it that just measures how much size change it goes as we heat it up. And this is showing you that as you're heating it up, look at that. This is in 573C is the equivalent on quartz as well. But you can see the going up in temperature, it did its expansion, come back, going down in temperature, it did its reduction. And all of that, again, leads to stress in the product, and whether that stress is beyond what your product can absorb will dictate whether you get a crack or not. Cooling cracks.
Decrease the amount of damage done by making finer quartz? Is that what you're...
If you can, or more often than not, is to say when I'm going through that temperature range, I'm giving more time for things to move and move slowly to go through it. So everything, because you can think about it, you're going to get movement in the product as you're changing the size. So if you go slower, it gives time for guys to kind of shift around a little bit and reform their glass bonds and get happy. And
So really just the best way is to slow it faster.
typically, that's the typical response on quartz, is to look at the rate, and because actually coming up with a way of getting the quartz out or grinding it, if you go grinding, now you're going to change this particle size distribution of your product, and you may create a whole new bag of worms.
Okay.
So more cases than not, it's either looking at reducing the amount of that material that you're using, or looking at the curve to say, can you adjust your firing curve to compensate in this region?
Okay.
Cooling cracks. Any changes? Change in materials, adjusting formulas. Where are cooling cracks? Look at your schedule to see, okay, is it something that's changed with that? How much load you have on it? Is it a matter of it's actually a mechanical issue that's causing the cracks, that's not allowing the brick to either cool uniformly, or there's loads on it that are basically overloading certain areas. Quartz distributions, this one was thrown in, but this is just showing differences between a couple of different materials. For a dilatometer study that was done, again using these little 1-inch bars, is just to show that no matter what schedule you're firing on and going up to higher temperatures, shrinking the product more, that quartz is still there. It's always happening at the same temperature, always going through the same phase change. So adjusting the actual temperature you're firing to isn't going to affect how the quartz actually responds. It's more what you do going through this temperature and how you mitigate the stress going through that temperature, which usually is go to a slower rate or pass through that temperature range. Need to understand the cause of cooling cracks. Should be able to identify and locate them. Identify the process variables, again, understanding your process when it's working sweet. And then when you do have an issue, go back and compare what changed in the process. Determine material changes if applicable. Document good performance. Baseline. Line pops. Selective mining. Finding or finer grinding. Again, if you have a lime pop and you grind it finer, it's no longer big enough material to actually cause an issue. It'll get distributed in the material. Fired brick plus steam. Basically, you're just looking if you can get it to pop beforehand. When you put the steam into it, you're trying to get the lime pop to grow and actually erupt. Pyrite pops. And these issues, again, are coming from mineralogical issues during mining, to where you've run into a seam that has these materials in it that aren't breaking down in your raw material processing, and you'll discover them when you fire it. Pyrite pops, again, this is just showing some of the chemistry that's going on of the pyrite and ways of addressing it. You can do selective mining, that if you know that there's an actual area of where these are coming from, then you can avoid the area, or finer grind that material more to try to break the pyrite up into much finer material, so that, again, when it's distributed through it, it doesn't present itself. It doesn't actually present an ugly spot. And more efficient firing may lessen the effect, but typically it won't get rid of it. So you might be able to get it to separate out or blend in a little better. Range and physical properties within a run and from run to run. You can have size variation, color, absorption, compressive strength, efflorescence, and coring. Solution to range, or solutions to range, is reducing the temperature variation, obviously, to where it's always easier to say than to do, but that's something to think about when you're doing it, is what's going to give me better circulation around the product and through the product. Reduce the atmosphere variation, again, circulation. The more you keep the stuff circulating, the more even typically you have. Control pressure and draft. Control where the draft is coming from. That if the draft is coming down the kiln, that's usually acceptable. If it's coming past your seals, not as much, because then you'll form cold spots and you'll end up with other issues on the kiln cars. Eliminate leaks. Check and document. And again, this goes back to things are running great, collect as much information as you can. That's different. It's kind of like a surprise one. This basically is just to keep in mind that you're trying to hit a color, but there's also so much more going on with your product, with your brick, that you have to keep in mind that if you stay so focused on color, something else could drift outside. So this is looking at to where our color range is here, but for the cold water absorption, we have to be careful, because if the material shifts a little bit and we're still trying to meet color, this line could shift over, and then soon if the line shifts this way with the materials going in, your color may drift up this line and actually end up in a higher absorption that puts you out of specification for 216. When to test particle size. New mining locations, new site or pit, when you're building a stockpile is a good place to look at it. And then anytime you're doing a mix change is a good place to look at it. Again, the more data you have, granted, it takes time to collect the data, but you'll just smile when you do run into a problem, because then it gives you something to look at rather than just guessing. Plant problems, shrinkage, size, drying problems, changes in physical properties or quality, the change in extrusion performance, green dry strength, and basically, according to Dr. Robinson, any problems. Always go back to particle size, look at your particle size, collect your particle size, smile at your particle size, live with your particle size, be your particle size. But once you go through and start doing that, that's when you'll get, John probably went through the kind of the golden ratio to start off with a third, a third, a third of clay, sand, silt. That's a good starting point. However, the chances of your material actually being on the golden ratio aren't extremely high. It's probably going to be close, but it's not going to be a third, a third, a third. So the big thing is again, by collecting data and over time, you can go through and actually determine where your green box is to how much silt, how much clay, and how much sand is your operating area, your suite area. And when you build that going forward and you're taking your data in on the particle size as you're running regular productions. You haven't had a problem yet, but all of a sudden you've now drifted over to here. You know that you're going to need to watch and make sure that all of a sudden I've got 10 or 33 cars in the kiln, and the first one just came out and there's a major issue, and now I'm in for a world of hurt because I also have my dryer full and I got everything else full. So that might be where you actually say, okay, let me take this material and we just try to run some of it, whether it's through a carver press or something, and stick it on a kiln car and send it through. And if you do control samples that way of the good product compared to what your little dot out here is doing, you can hold them side by side and just look at them and say, okay, is there a difference? What's going on? And again, it may not tell you that there's going to be an issue or if there's going to be an issue, but it's another data point that you can look at and figure out, do we potentially have a problem? And that's it. Oh, I know it's a lot. It's a lot, but the big thing, I guess the big thing that I'd want you to take away from is, again, if your plant is running well right now, now's the time to really start hopping and gather as much information as you can and really understand.
And most of my work on. I started out when I was a student working on fluorine. I've worked on sulfur, worked on chlorine. Now we're working on mercury, so they keep adding to the list of things we have to worry about. And we keep doing work as it goes along. But there's some emissions that we commonly have from our material, just because of what they are. Fortunately, all of them are a really low level, okay? Fluorine is probably, well, sulfur can be high depending on where you are in the country, but fluorine is probably the most common. It's in part per million levels. So part per million, basically, if you want to figure out if somebody tells you it's 60 parts per million, or divide that by 10,000 and that'll tell you how many percent. So it's a very small percentage. But it's enough when you add up the tonnage. We need to control it. And fortunately, fluorine's very easy to control. Chlorine, the stuff in South Texas happens to be some of the highest chlorine materials we deal with. So you've got a corrosion problem. You were talking about in your dryer, it's because of chlorine, okay, in the raw material. Yeah. So that's just the nature of the beast. The guys up in Ohio, they have a lot of sulfur naturally in their raw material. Any of you have any kind of, in your ductwork, your exhaust ductwork, you get any black or green gunk that builds up? Okay. That's actually a form of sulfur. It's an ammonium sulfate. It can be a chloride, an ammonium chloride, that forms in your exhaust. It's called a condensable particulate. And it collects in those spots, and yeah, it's nasty. But that's not regulated, and we'll talk about why in a minute. Carbon. Well, no. Well, the real answer is EPA has two lists of pollutants that they look at. There's one list they call criteria pollutants, and that is carbon monoxide, sulfur dioxide, particulate matter, lead, okay, and that goes back to when we had lead in gasoline. That was pretty prevalent in the environment. And NOx. Okay, I'll talk about NOx in a second. And then there's a list of 140-something HAPs, hazardous air pollutants. Fluorine and chlorine are on the HAP list. Ammonium chloride and ammonium sulfate aren't on the HAP list, so EPA hasn't regulated those. The nice thing about those, I mean, they are corrosive, but they condense the ammonium sulfate and ammonium chloride, and you don't, for the most part, you don't emit them the same way you might with these acid gas. They stay in the ductwork more, so and foul things up. So you can have, depending on, we talked about flashing, and you use that to get those reduction colors. But you can get some organic stuff. I mean, if you're flashing really hard, you get a soot plume, right? Okay, that's what we're talking about here. And some of that stuff, depending on if you got somebody who really wanted to be difficult, they might find something at really low level in that you'd be concerned about. But for the most part, we don't worry about that.
So
NOx, yes.
Flashing just in general, it's not really adding a whole lot as regards to the major things that we're looking for in emissions?
We just mention it because sometimes it comes up. It's more of an opacity issue because there's also in your air permit, there's probably an opacity clause.
Yeah.
So it has to do with can you see through the plume or not. And that would contribute more to that, any kind of sooty emission.
But as regards to like the hydrochloric acid and,
No, you're not adding to that.
okay, but
Probably not.
Basically, all that we're adding is soot
Yeah.
on top, and then we're not accelerating the creation of those others.
No, that's coming from your raw material.
Jim told us when we were up there in that class, he said, there's 5 years y'all aren't going to be able to flash. And
Yeah.
the guy from Prince was like, yeah, so we're going to sell y'all all this stuff. And,
Yeah.
like they were kind of, together on it. Or whatever.
No,
Did you hear him
it's
say
just
that?
no. We deal with the lady from BIA who does all the EPA regulation work, and she's the one telling us that this opacity thing is going to come around eventually. So, and then Prince has heard it, and they just jumped up and said, "Hey, we can help."
Yeah.
Yeah, but I don't think they're driving it.
Oh.
NOx is a tough one to deal with. Okay, and you've had some NOx issues here, haven't you? At some point? Okay. So with criteria pollutants, you have, mostly comes from cars, you're right. NOx is what they call a criteria pollutant. So particulate matter, SO2, those are the other criteria. And their area averages. And ozone. You have ozone action days probably if you live here around Dallas. Anybody ever heard that term? Mm-hmm. Okay. It means the ground level ozone concentration is too high. It's bad for people who have asthma. Most of the ozone's coming from cars too, or from car exhaust. But it's hard to regulate cars, so they come after plants. NOx is created anytime you heat air. Okay, remember air is about 80% oxygen or nitrogen, 20% oxygen. So you heat it up, you get above about 2,000 degrees, and you start forming NOx. The hotter it is, the more you make. Okay, it's just the two combined. And NOx is a whole family. It could be NO, NO2. There's also an N2O. That's laughing gas. You aren't really making that, but it's either NO or NO2 mostly, and it is a precursor for making ozone. Okay, so once it gets in the atmosphere, it reacts with oxygen to turn oxygen into ozone. So the two are related. This is the only one of these that is difficult to deal with because it's just a byproduct of heating air. It has nothing to do with your raw material, has nothing to do with anything but the fact that we operate at high temperature. So that's something in the future we'll have to think about. The thing EPA is all over us about right now is metals, okay? And the biggest one of that is mercury. So we had to buy a piece of equipment to measure mercury to part per billion levels, okay? So whole industry's making a few pounds of mercury a year. And they're wanting us to regulate that at a huge cost.
It's crazy because I used to work at Safety Clean.
Yeah.
And we just, the incinerator was down here in Texas.
Yeah.
And they just basically burn everything.
Yeah.
Which I don't see how it keeps it out of the atmosphere, but they put it in a box.
Yeah.
They bring it here and they burn it. They're supposed to keep it out of the air. I don't know how.
They're supposed to have some sort of, a lot of emission control on it to keep it from going up to stack. Yeah. Incinerators have their own set of rules.
Yeah.
So, but mercury, when I was a kid, we played with it. But now it'll kill you. So,
All those lights are mercury.
yeah. And there's no way to recycle those things.
Yeah, we put them in a box. People
Yeah.
come to us, we put them in a box. All those light bulbs, and they bring them down here and they burn them.
Okay.
So, I mean,
So you're emitting mercury. The big emitter for mercury is actually coal-fired power plants. There's a fair amount of mercury in coal. It tends to accumulate in higher mammals like us. And you eat tuna fish and stuff, that's supposed to be a good ingestion or way to get mercury in you. And you don't really have a means of getting it back out. Your body just accumulates it and holds on to it. It gets high enough. You ever heard the term mad as a hatter?
Yep.
Okay. That really came, or the Mad Hatter from Alice in Wonderland. They used to use mercury to cure felt. And they noticed all the guys who made hats would eventually have neurological problems. And somebody finally figured out it was coming from that. So there's all kinds of interesting stories about stuff like that. Like some of the first treatments for syphilis, they would give you arsenic to a level that was just below what would kill you. And the theory was if it almost killed you, it would kill all the little stuff living inside you. And so, you know, I had a chemistry professor who had all kinds of good stories like that. So fluorine, if you remember that crazy chemistry thing I showed you yesterday, the crystal structure for clay. Mm-hmm. So there's those hydroxyl groups, the water groups. Fluorine is the same size and charge. So just when that clay was forming, occasionally a fluorine stuck in a hydroxyl spot. Okay, it's called a substitution. So the fluorine mainly comes out when we get into the part of the preheat where the clay mineral breaks down. It is emitted at that temperature. So some people talk about, there was a lot of discussion when fluorine first started to be regulated. There's actually a little bit of a cycle that goes on in your kiln. It comes out in the preheat, it gets pushed back toward the cooler wear coming in, and some of it's reabsorbed in the brick. It's not a huge effect, but it does drop the overall emission a little more than you would expect. But we don't really concern ourselves with that. There are ways to capture the fluorine in the brick. If you have a little limestone, it's not unusual to have a lot of that fluorine stay in the brick. Problem is, it also holds on to sulfur, and you can end up with efflorescence like we talked about. So, yes?
If we breathe that stuff, what does it eat?
Fluorine, the levels, the thing I always look at when I go in a brick plant, I look at the glass in the control room over the kiln. Is it real frosted? If it's real frosted, there's some fluorine in the air.
So it's not sulfur, that's fluorine?
That's fluorine that does that.
We change ours out every year and a half, 2 years.
Yeah.
We always assume, I always call it sulfur burn, because it was like it's into the glass.
Yeah.
Scraper and scrape out.
Yeah, that's fluorine. There's never been any documentation of damage from that. Fluorine just has those kind of effects. And now, if you get it eats glass.
Okay.
Like the things like you do like headlight, glass
Yeah.
headlight.
Yeah. So,
Repel works for a little while.
yeah. So fluorine, if you have the silica and glass, they have a special affinity for each other, and you make silicon tetrafluoride gas that goes away. So it actually eats glass. But people have been making ceramics and pottery since it's one of the older professions. I won't say it's the oldest. You know, that the obvious one in teaching, yeah, it's in the top 5. Let's say that. Okay. There's not been any documented problems. Now, if you're dealing with liquid HF, which you're not, you're dealing with low levels in the air. Liquid HF can damage your bones. Okay, if you get it on your skin, and we actually use it in the lab for this very reason. If we, like some of that equipment I showed you, if we have a piece melt, you can put it in hydrofluoric acid and it'll eat the glass off of it, and it'll leave the alumina glass or the parts for the thermal analysis equipment behind, and it cleans it up real nice. So we use it. But if you spill it on yourself, it doesn't necessarily burn your skin. It goes through your skin and it starts to deteriorate your bones. So it's bad to deal with the liquid form of it. But I'm not aware of any damage caused by just having it at low levels in the air. So it's interesting stuff. So just some examples of where we've done some emission work. This is that thermal analysis with evolved gas we talked about the other day. And we're seeing this red here is the HF, and we're seeing it at the same point mostly as the water vapor coming off. There is some overlap. And then in our lab test where we have a very dry environment, we also see a little more at high temperature. But that has to do somewhat with the way we measure it. Chloride. Chlorides can come from 2 sources. In your case, it's probably in the salt. okay, that's natural in your material. I'm not a geologist, but I think parts of where you, or South Texas, were once, underwater, okay? Same as where I grew up along the coastal plain in South Carolina. And because of that, you got a lot of salt. There's also chlorine associated with organics. And there's some that EPA was really worried about, this dioxin and furans and dioxin-like compounds, and they made us do a ton of testing. You probably got involved in some of that, where they went around and did stack testing, but they never could find evidence of this, which is a good thing. Dioxin's bad. The number one source of dioxin exposure for people is backyard trash burning. When you burn plastics, you're exposing yourself to those, and they're not real good for your.
You don't stand around the fire. You light it up.
Yeah, okay. Don't breathe that smoke. Okay, it's not real good for you. Because if there's plastic in it, it's not real good for you. And there are all kinds of dioxin compounds, but we've done a lot of testing on that. But this would come out in the early preheat. The salts would come out probably in the soak, or the chlorine from the salts would come out in the soak. Do you usually, for fluorine and chlorine, do you emit everything that's in the body? And the answer is no. We do something called a mass balance test to estimate emissions. So we measure the fluorine and the chlorine on what's going in the kiln, on your raw material. We measure it on your fired brick. And you can see, depending on where you are, 50 to 60% of it can stay in the brick. Okay, I'd say 20 to 30 is more of an average retention rate, but we assume the difference is what went up the stack. So these are very common. Chlorine, so an average fluorine number is going to be somewhere between 600 and 800 parts per million in the raw material. Chlorine is going to be somewhere, commonly, is going to be somewhere less than 50 parts per million, but in some of the materials here, it can get up around 200 parts per million. But we're talking very, very small numbers. But when you talk about tonnage, it does add up. We've already talked some about sulfur. Sulfur comes from two sources. Pyrite oxidation, so pyrite's that fool's gold or the marcasite. And ideally, we're getting that out in early preheat. We're not leaving it behind, but we commonly see that this gets partially converted to sulfate, and then it comes out later in the cycle. And then the sulfates we talked about that are coming out slowly in the soak. So it's always, we're happy for fluorine and chlorine when we get retention because it doesn't hurt us. It just cuts down on emissions. Sulfur, you're always better off getting it out of the body and dealing with it in a pollution control device or something, because any sulfur you leave behind in the body tends to be an efflorescence risk. Okay, so if you don't want to see efflorescence, it's best if you can get it out if possible. Although this is not easy to remove. So just a little repeat of what we've seen before. This is sulfides. There can be either one of two steps, but it picks up oxygen. You get to an iron sulfide, an SO2, and then it goes through a second step to give you iron oxide and 2SO2. The problem here is it takes a lot of oxygen to make this happen. It consumes a lot because not only does the iron need oxygen, the sulfur needs oxygen. So it takes a lot to drive that to completion. So that's why it usually doesn't happen. This happens on its own just from temperature. It doesn't need any additional oxygen. You get it hot enough, it will start to decompose. But for whatever reason, it doesn't happen fast. So this is sort of a tree, Christmas tree of all the stuff that can happen. So what we want to happen is we want to go from the pyrite directly to the iron oxide. And what usually happens is we go to this kind of sulfate thing if we're moderately oxidizing. And then when we get hot enough, hopefully that decomposes to iron oxide. If we're pretty reducing, we can actually go this direction. So if there's a real deficiency of oxygen And this stuff really causes havoc with efflorescence if we get into those kind of compounds. So it gets really messy, and there's a lot of talk about this. And actually, the pyrite isn't stable in air. Once you dig it up and expose it to air, it starts to do this as much as it can on its own. Okay, there are places out west where they're mining, it's pretty well known around copper mines and tin mines. There's a lot of pyrite in that, and those tailing piles, when they get wet, they make sulfuric acid. Okay, so they have to have special controls. So that sulfur becomes, with water, becomes sulfuric acid and can damage streams and plant life and all that kind of stuff. So it's something to look out for. We don't have enough pyrite to generate that level in a pile to generate any level to worry about. But it will sometimes pre-oxidize. So there are people up north who have this. It's easier to oxidize this than this if you have enough oxygen, so they don't stockpile their material. They dig it out of the ground and go straight to the kiln. Because if they let it sit in the pile for any period of time, it actually gets harder to get all the sulfur out. The problem with not stockpiling those, you gotta be very careful in your mining, or you're gonna have all kinds of variation coming through the plant. So this is, if we've got pyrite, this is where pyrite comes out. I don't have a temperature on that, but this is going to be the early preheat, usually right before the clay mineral breaks down, and then the sulfate starts late in the preheat, or late in the preheat, early in the soak, and kind of persists through the soak. So, like I said, we do balance measurements, and this is actually a test I lifted from when I was looking for a way to measure fluorine and chlorine. It's so small, it's hard to get it out, it's hard to measure it. But this is called a pyrohydrolysis. I stole this idea from the people who deal with nuclear salts. Okay, they want to know the fluorine content in uranium salts, and they came up with the method. But basically, we heat the sample up in a tube. We got steam flowing through. We catch the condensate off the backside of the furnace, and we can read that with another instrument. We use those ion chromatographs like I was telling you about for the soluble salt. They can measure really low levels of fluorine and chlorine, and it's similar to a stack test method, that analysis technique. Any of you ever seen stack testing in your plant? Yeah. Okay, so that's a whole art in and of itself. But basically, depending on which method they did, at the end of that, to measure the fluorine and chlorine in those glass things, the impingers at the end of the train, they use the same method. So we take the dry material and the fired material, and we measure the fluorine and the chlorine and assume the difference is what went up the stack. So new kilns that are very good at controlling air, no leaks, we can get correlations of up to 99% between what we measure in the lab and what the stack test says. The older the kiln and the more air leaks there are, the more dilution happens, and we tend to always be a worst case. So we're saying we can give you a number. It's like it'll never exceed this, basically. So this is one of the chromatographs. I don't know that you really want to see it, but basically it takes everything that you inject in the water and it grabs on to all the salts. This one does fluorine, chlorine, nitrite, nitrate, sulfate, and bromide. And what it does is, based on whatever the element is, it releases it off the absorption column at a different point. So fluorine comes off first, then the chlorine, then the bromide, and you can make your measurements off that. Same way that they make Dasani water, like I was telling you. They completely deionize the water, take all the salts out, and then they use these kind of things to add salts back and give it the right composition. Because the salt is what gives the water the taste. Anybody ever tried drinking distilled water? Pretty nasty. Yeah, doesn't taste good because there's no salt in it. So one thing we do with those mass balance calculations, we have to correct everything to a fired weight basis. Okay, so we know our material loses weight going through the kiln, like that LOI tells us. So we have to account for that LOI. So the results we give are usually pounds of HF per fire ton. Okay, that's called an emission factor, and that's what's used to report to the state EPA or whoever's doing your permit. There's a document called AP42 that was put together in the 80s. You can go and just type AP42 brick, and it'll pull it up on Google, and you can see what average emissions were at that time for the whole industry, and compare it to yourself if you're interested. Jim here's got the same instrument. This is a LECO carbon and sulfur analyzer. This is how we measure carbon, sulfur. We can differentiate sulfides and sulfates, organic carbon from carbonates, depending on how we set it up. But basically, it's a tube furnace, and I'm not sure what it is in Fahrenheit, but it sits at about 1375 Celsius, so really hot. Because remember, I told you the sulfates are real sluggish and decomposing, so we got to get it real hot to make sure they fully decompose. So you push the little boat in that tube furnace that stays hot all the time. It's got some infrared gas cells, and it gives us a number on the fluorine and chlorine. Y'all did that in the, I don't know if you were in there when Mark did it, but we measured it on your material in the short course.
Yeah.
Yeah.
He was a young guy back then. Though.
Yeah.
He was a really young guy.
Yeah. Oh, okay. It might have been Nate, or
He was
one of
just
the...
fixing to leave.
Okay, so one of our technicians or students did it, but we can measure carbon and sulfur this way. I don't think I have a picture of our mercury analyzer. So at one point we wanted to see what kind of variation we see in all these things. So one of our manufacturing members took apart a car, and they gave us samples from across the car, and we measured the fluorine and the chlorine and the sulfur. We did top, middle, bottom all across the car. These are the positions that correspond to this. And we're seeing not that much difference except for this one point, and that could be a sampling issue. On the dry, the fired had a little more scatter, and then the green's the difference. But when you do the average and you look at the standard deviation, it comes in pretty close. Chlorine looks like there's more scatter, but remember we're measuring a small number here. So we're measuring, up here we're measuring 800 parts per million. Here we're measuring more like 80 to 90 parts per million. And then sulfur came in very tight, again, because it's a bigger number. So this is now in percent. So this doesn't look like as much scatter. But typically what we do is we make a composite. So people will take a top, middle, bottom and give it to us. And we'll have 3 dried, 3 fired, or 2 dry, 2 fired. And we grind them together and make one sample for our analysis to take out some of this variation. So this is, we've done a whole lot more than this, but this is an example of how the stack test correlates to stack testing, our lab test. So stack testing value, pounds of emission per hour, this is for fluorine. This is what we estimate. And remember, I told you we're always higher, almost always higher, because of the leakage that happens in a real kill. But these 2 kills were brand new. They're relatively recent vintage, and we're dead on those. But we typically run, this one for some reason we didn't run higher. We were a little bit lower than what they guessed. But what we came up with, we were hoping that we could come up with, there was a general correlation factor. So if you needed a stack test and we tested your material, we could say, okay, if the correlation factor is 0.8, we would multiply what we measured by 0.8, and that's what you could give the EPA. But what we found is it really depends on the kill. Okay, so if you wanted to use this, and if your state would allow you, and we have some states that do allow this, you've got to have a stack test. We come up with a correlation factor, and then any further testing that we do, you use your site-specific correlation factor in your reporting. So West Virginia, parts of North Carolina will take that, and so we just do, instead of having to have periodic stack testing, we just do annual mass balance for them. So sampling obviously is very important in how good that prediction is, and we've seen some variation, a little bit of variation across the kill. The more samples we take, the more we combine to make a composite, the better we get. Fuel type, does it contribute to emissions? We don't think that it does for fluorine and chlorine. Obviously, depending on if you're using a solid fuel or something, it could contribute to sulfur emissions. But we don't really see much influence from fuel type. Age of the kill, okay, how much leakage there is, how much air infiltration seems to be the big issue that affects our correlation. Haven't really seen been able to find any correlation between topside and underfired or burner configuration. I'll leave. We haven't really found any issues from how the kill's operating. I've gone in plants to help with stack testing. One of them, the stack test, it was in Oklahoma, but it wasn't an Acme plant. The stack was so hot on top of the kill that we melted the fiberglass ladder we were leaning against it to do a port, or to measure in a port. That was not a very comfortable place to work. But we have seen a lot of issues with the quality of stack testing, and that's what the people who deal with EPA are working on right now in the rule making that's going on. So the way that the rules work, and I didn't think to include this, we go through something periodically called MACT. Okay, I don't know if any of you have ever heard that. Maximum Achievable Control Technology. So theoretically, they set a level for these emissions, and they say, okay, you have to put in control device or somehow come below this level. And every 7 years, they reevaluate it and see if there's new technology available, and they'll lower that limit. Well, they don't really follow the technology like they're supposed to. They just lower the limit and expect you to come up with the technology to meet it. So that's a philosophical discussion that goes on with EPA. But we had a rule, and most of you put in the early 2000s, most of you put in some kind of control device, and then a judge threw that rule out. Okay, so we were operating with a no rule situation, even though we'd all complied with the rule we thought we were going to have. And now EPA came along and said, okay, we're going to use the control numbers to create the new MACT, where that rule technically never existed, but they don't consider it that way. So there's a lot of arguing going back and forth about where the levels need to be, and we have a proposed MACT rule that's come out. It's not as bad as we thought it was going to be because some people have worked really hard on behalf of the industry. Garth Taylor, if you met him, is part of that team. And they've really been fighting that to try to get a fair rule from the EPA.
Can plants meet that standard without a scrubber?
It depends on your raw material, and it depends on your tonnage. So there are ways, and that's a whole nother really complicated argument, but there's something called a synthetic minor, and basically if you stay below a certain emission rate, usually by not processing more than a certain amount of material, you may be able to get away with no control.
I think what they're doing at our plant is they tested B plant with a scrubber and A plant, and they're trying to average them together to use that.
Yeah.
I don't know if they're going to be able to do it.
Well, it has to do with, yeah.
Huh?
It's your total sources on your facility.
It's part of, you do modeling and you figure out what your fence line concentration is. And I think, like what you're saying, if that fence line concentration is below a certain level, they may be able to do that.
That'd be good.
Are those standards, does it look like we're going to, with a new MAC, are we going to be inside the standards? Or?
I think most people are going to be okay except for mercury.
Still trying to figure it all out.
Yeah.
We tested 3 times.
Yeah.
I'm the plant that we tested 3 times.
We're chasing a moving target on it. So the people that work on it are working on it around the clock.
Oh, yeah.
So, but the one that seems problematic with the whole thing is mercury. And we're chasing nothing there.
Have we figured out how to control the mercury?
I don't know that anybody really knows how to control mercury yet.
There's the problem.
Yeah, because, well, that's part of the argument with the MACT, because it says maximum achievable control technology. There's not really demonstrated technology for controlling mercury, but they put a number on it anyway. Yeah. So I would say this whole thing's going to end back in the courts, and we may not see a rule in our lifetime.
It may be like we would.
Yeah. But I think, you know, the controls we've done, I think we've made a big hit in the emissions. I don't think there's much left there to worry about, but EPA won't walk away with nothing. So you got to give them something. I don't know what that is. So just a little idea on how scrubbers work and what goes on in there. So there are two types of absorption that take place. A chemical absorption, that's mostly what we're seeing with the HF. It wants to react. So I don't know if you like when you take an antacid, okay? That is a basic material, okay? It's a base. We're combining that with the acid in your stomach and you make salt and water, okay? You neutralize it. We're doing the same thing in a scrubber. We've got your limestone, which is basic, and you're putting acid gas on it and you're making something that's neutral, okay? And we're reacting to do that. So there's chemical absorption and then there's physical absorption. Some things like chlorine and sulfur, sulfur because of the size of the molecule and chlorine just because of chemistry, don't react as quickly as the fluorine. And you have to help them. So some plants, I don't know if any of you, you pre-treat like if you've got a dry injection system, sometimes you pre-treat it with water, okay? The water helps to hold on to that stuff while it reacts. There are different ways of doing it, but it's a slower thing. The other way this comes into effect, if we do ever have to control mercury, really high surface area carbon, activated carbon, okay, use it a lot for odor control and things. Seems like it will pick up some of it, but how do you introduce it in the system without burning it up? That's part of our problem we're trying to figure out. It will hold on to organics, and sometimes it'll hold on to metals with that physical absorption. So on your in your scrubber reagent, ideally you've got something, and this is a balance. You want something that's got what we call surface area or porosity, because the surface is where this stuff reacts. And I'll show you some actual pictures of what it looks like in a minute. But this is just an example. So you've got your molecule coming along, and it's trying to find some fresh surface of that reagent to sit on, and it reacts. So the more porosity you have, the more area you've got for reaction. We do tests called surface area, where we can measure that. So you can, if we get limestone, there's a whole range of it. You can get marble chips, okay? They have essentially no porosity, and they tend to be not as good as scrubber reagent. The best one I've ever found is actually a fossilized coral. There's a bed of it in coastal South Carolina. It has a very high surface area, and it'll pick up more fluorine than anything else we've worked with, because we've actually done a lot of these kind of tests. The problem is you don't want something that's so soft that it crushes in your scrubber. You want something that stays together. So you're trying to balance strength with porosity when you buy that scrubber reagent. They're now making some synthetic ones in Germany that have a huge surface area, and they're very effective. I think some of them incorporate some activated carbon. Probably if we ended up having to control mercury, we might have to start buying that stuff. But we'd have to see. So for fluorine this helps with fluorine. Fluorine will keep going through any reaction skin you get after you pick up the acid gas. Chlorine won't. Chlorine's too big. Chlorine only absorbs on the fresh surface. Sulfur also. Sulfur actually has the highest driving force to react with limestone, but because it's so big, it can't, once there's any reaction on that surface, it can't penetrate through it like chlorine or like fluorine can. So if you have a lot of sulfur, you probably got a powdered lime system where you're injecting that and you got a bag house. Anybody got one of those? Yeah. Okay, it's because you got sulfur in your raw material. The only way to pick up the sulfur is you got to have a lot of surface. You got to have a fine powder. If you're just dealing mainly with fluorine, the box of rocks, the dry lime absorber, works just great. So a lot of chemistry here. We won't really worry about it, but mainly if you've got a DLA, you're taking the HF out of the gas and you're making calcium fluoride that's not soluble. It's very stable and it just hangs around, and you can do with it whatever you want. Calcium chloride is soluble. We make a small amount of that, but we don't really worry about that. And calcium sulfate, gypsum, it's actually a lot of the scrubber reagent goes to farmers and they use it to modify soil pH, and it's just fine for that. We've actually had the people in that ag department at Clemson do a bunch of work and never found any problem. The dry lime scrubbers or the diff types, we're using either a hydrated lime. Some people use a sodium bicarbonate. Same reactions for the most part. We're making the same things. We're just using a powder to do it. One of the plants up in Ohio, they have a shale that's low sulfur, and they have a fire clay that's very high sulfur. And so they actually read the concentration of the gas going into their scrubber, and they use that to, this is very expensive and this is pretty cheap. So they try to control with, this is their primary control, but when fire clay starts getting in the hot zone and the sulfur starts to go up, it triggers a feeder for the bicarb to bring the sulfur back under control. Once it falls below the level where they want it, the bicarb shuts off, and then the calcium hydroxide kicks back in. We had one company in the Dakotas, I think. They were trying to use all sodium bicarbonate, and the feeder got out of control, and then they weren't getting flow through the scrubber, and they opened it up, and it was a block of salt, the whole thing. And they chipped out a sample, they sent it to me, and they said, you got to help us. This stuff is crystallized in the scrubber. We got a huge problem. So I was, to do the testing, I put some in water. In a couple of minutes, the water was clear. So I said, go get a fire hose and start washing out the scrubber. And, basically this stuff's really soluble. It's kind of nasty to deal with, but it's very effective for picking up sulfur. Some people have played around with magnesium hydroxide, calcium hydroxide. There's only one operating wet scrubber in Utah that I know of. The problem with the wet scrubbers, what do you do with all the water that you make out of it? They can be very effective for particulate and for chlorine and sulfur and everything, but they have to have a separate water treatment plant on site to clean up the water before they let it go.
Go back. You guys know what you're using at your plant? You guys understand? Sealy?
Yeah.
You got the first one.
Yep, the
Box of rocks. Dry lime absorber, box of rocks. Sealy's got one, Texas clay, right? Has a box of rocks.
That's right.
And I guess the rest of you have dry lime scrubber. Denton? You got the second one, dry lime scrubber.
Yeah, because of that gypsum you've got in your raw material, you'd have some sulfur in your emissions.
We experimented with the
We just got a kiln exhaust stack.
Okay.
They don't have a scrubber.
Okay.
You don't have a scrubber, okay.
You got the dry lime scrubber, but like John said just a minute ago, at one time you were adding water, right? To make it more effective. You're still adding water there. So that one, dry lime with water addition.
Yep. Is that the Soleil or
Yeah,
design?
What?
original process there.
Crossadere.
Okay.
Built it,
Yeah.
Right, and Elgin New Plant, over Elgin, that plant you're from, they've got dry lime scrubber. Washita's got dry lime scrubber.
Mm-hmm.
Who am I missing? Who's here?
Oklahoma City, we just have a kiln exhaust stack.
You don't
have a scrubber.
No, we don't have a scrubber.
Yeah.
We got a wet scrubber too.
Yeah. No, the only one, Interstate's the only one I know that has one. Did you go on that tour and see that one? Okay. They got a water treatment plant on site too.
We got a wet scrubber
You
on
do?
our calciner,
Okay.
and we run sodium hydroxide.
Yeah,
Okay.
On our rotary kilns, we do a wet scrub.
Yeah. What do you do with the water?
Well,
We have a big containment pond,
Okay.
That we have to
Yeah.
check the pH constantly in, and
Okay.
add sodium hydroxide, we call it caustic soda.
Yeah,
And so
to keep it neutral.
keep, yes, keep it
Yeah,
neutral.
okay, that works. I didn't know you had to do that on your calciners.
Yeah, all our calciners.
Okay.
A wet system.
Okay. So what do we look for when we're looking at a reagent? First thing we want to see is, does it have a good chemistry? And usually that's the calcium content. Is it got a real high calcium content? And we can do chemical analysis on that. Sometimes we've seen them where they're supposed to be calcium and they got a lot of sand in them or something like that. Anything that's not calcium, and to a lesser extent magnesium or sodium, doesn't do anything. It's not helping you with the reaction. So you want a high purity there. And depending on what kind of scrubber you got, that's either going to be a limestone or a hydrated lime. This is calcium carbonate. That's calcium hydroxide. Similar, but they're just you just have to make sure you're getting what you expect. And that's pretty easy to do. The other part is this surface area, and it's a pretty easy test to run. It's not.
Oklahoma Water Works good stuff like the calcium.
Okay. So this is, we're not so much worried about this for a DLA. Usually they'll work okay, as long as there's some porosity. But for a dry lime absorber, or for a dry lime scrubber, we want to get that porosity and surface area up as much as we can, because it really improves that SO2 efficiency. So this is an example I was telling you. We had a place that was using the marine limestone, we call it. They went, their vendors said, oh, I got this better limestone, it's great stuff, you need to try it. They had a stack test and they were way over their limits, okay? And we started looking and this stuff just wasn't really reacting that well. It was too dense. So they had to go back to the marine origin and do another stack test, and they weren't real happy about that. So there's some easy tests you can do on the porosity or density and the chemistry to make sure you got what you're supposed to have. But this is what it actually looks like. This is from a DLA. So this is the limestone, and this is showing you the skin that develops on the surface of the limestone. So some places used to have peelers. I don't know who's still doing a lot of peeling. You know, okay. So what you're trying to do is you're trying to knock that skin off and leave fresh surface for the scrubber, or for the acid gas to get to. Yep. So this is showing the concentration of fluorine. Basically, the bigger the line, the more fluorine. And it's kind of overlaid over here, so you can see that bright, shiny layer's got a lot of fluorine in it. It's got a little bit of sulfur in it, where it's picked up the sulfur. And then it's got a very small amount of chlorine. So in order of preference, based on the studies we've done, it wants to pick up the sulfur first, okay? And it will pick up sulfur on any fresh surface it can. It wants the fluorine next, and it'll take the fluorine, but remember, fluorine's small enough that it'll keep penetrating. And you can get pretty thick skins on these things with fluorine. And it'll pick up chlorine last, mainly only on fresh surface that the other stuff didn't get. So chlorine's pretty weak in absorption. So this is an example of a dense limestone. I think this was before peeling, and then this was after peeling. I wanted to see, nope, I got an example coming up. So you can see where it knocked off some of the skin. This is one of the real porous limestones. One of the things I always think is interesting is you notice how that layer is thicker wherever there's usually some cracks or some voids. It seems the gas seems to follow those, and you get more reaction. So that's the difference. That's a porous one, and that's a real dense one. You just don't get as much reaction. So we've already talked about this a little bit. This is scrubber types, a dry lime absorber. Basically, you've got gas coming in, and you've got limestone kind of trickling down. Usually there's some cascades, and you're trying to get good gas and reagent interaction before that gas escapes. And typically they work extremely well for fluorine. Let's see, dry lime absorber aren't as good for SO2, just like we said, but they're very good for HF. This is some work. This is Gary Parker, who works with me. We were testing different reagents, and basically what we were doing here, this was we scheduled this week. This is at Palmetto Brick. It's on the eastern side of South Carolina, just below the North Carolina border. A tropical storm stalled right here the week we were there. And my boots held out for about the first 3 days because we were out in the rain all day. And then they started to leak. And any of you ever heard of jungle rot? You know, by the end of the week, I found out what that was. It was pretty unpleasant. But basically, when you do the stack test, this would be the stack. There's a little filter holder that they have filter pads on. I don't know if you've ever got to see this to do particulate. We basically stuffed those with different reagents. And we drew gas out of the stack, and then we'd take them home and we'd see how much fluorine we picked up. And we were trying to figure out what was the best reagent. It just wasn't fun going up there to change that thing in and out. So we spent a week in the tropical storm doing these kind of things. So it was pretty interesting. So basically, this is the basic flow train when they come do the stack test. This is the probe that goes in the stack. It's got a heated line so you don't get any condensation. And then this is the filter pad. So when they're measuring particulate matter, that's where they're taking the sample. Then that comes, there's usually a group of collection liquids, and depending on the test, they're different liquids. But a lot of the stack test methods use this. And then you've got some sort of pump and volume meter. And so what you're trying to do is you're trying to draw the gases when you're doing particulate. So if you've got particles flowing by your nozzle, so I've got my nozzle in the stack, and I've got particles flowing past. I'm trying to sample them at the same rate they're flowing past. Because if I'm pulling too much vacuum on that, what happens is like a particle that's going here that should go past gets sucked in. So I oversample the particles. Okay? If I'm not pulling enough gas, then I've got a particle that's coming, floating by, that may have normally gone in, but because of turbulence, it bypasses that nozzle. So you're trying to do something they call isokinetic sampling, and there's a whole routine you go through. But you collect the sample for a period of time. You take that filter pad and you figure out how much particulate matter you had, and then if you're doing fluorine and chlorine, you analyze those liquids and you figure out how much you collected. I've been doing a bunch of stuff lately where I take those filter pads and I've been looking for trace metals. So I go to the electron microscope lab and I see a lot of that sodium or that ammonium sulfate we talked about gunking these things up. It's pretty interesting. I don't think I have a picture in here of it, but haven't been able to find any metals in that, so it's been really good. But what we did is we actually stuffed that full of different reagents. So we did a run with nothing in there, saw how much fluorine we collected, and then we stuffed them with different DLA reagents, and then we measured what was in, and by difference it told us how much we picked up. So we were looking at, and we looked at different temperatures, and so we had our basic limestone, and this work was done when chlorine was first coming on the scene, and nobody knew how we were going to capture chlorine because we knew that limestone didn't do a real good job. So if you already had a DLA and they dropped the chlorine standard, how are you going to comply? And so what we were looking at, these are some synthetic reagents that come out of Germany that they make. Basically, if this has surface areas measured in square meters per gram, so a normal, like a marble, is going to have a couple of tenths of a square meter per gram. A good limestone is going to have 2 or 3 square meters per gram. These things are in the 100 square meter per gram. Okay, so they're real porous, and the way they make them, they're still reasonably strong. But for fluorine, we didn't see that much benefit. It wasn't really worth the cost. For chlorine, it was huge how much extra, and for sulfur, we picked up a lot more on these reagents. One of these, the sorbelit, actually has activated carbon built in, so theoretically we've never gone back and done this. But theoretically, we should probably be able to pick up some mercury with that if we ever had to. One of the things to note here, these were actually from lab tests we did, where we had HF flowing and we were measuring how much we were picking up as a function of time. And you notice all of these, for the most part, come up, and for fluorine, they stay at a certain constant level, saying that the fluorine can kind of keep swimming through that reaction layer. For the sulfur, you get a peak and then it tails off. So as you build up that reaction layer on the reagent particle, it gets harder and harder for the sulfur to pick up. Okay, it just can't penetrate through like the fluorine did. That's why you need a powdered reagent like you do in a DIF. So dry lime scrubber, basically there are different ways to do it, but you inject a powder in, you have some sort of reaction chamber where you're trying to get mixing of the powder in the air, and then you typically have a bag house to take that powder back out. A lot of the reaction takes place on the bag, so you probably have a delta P, a pressure differential that you try to maintain. Periodically you have to knock the bags and clean them. You lose a lot of efficiency until that cake builds back up. But forcing the gas through that cake, even though it takes energy to do that, usually helps improve the efficiency of those things. They're different designs. This is one with a conditioning drum where you might wet the reagent before it goes in and you get that reaction. Wet scrubbers, like we said, there's one that we know of. So you've got the gas flowing up, droplets coming down, and hopefully you get mixing with those droplets, and you might put a little bit of reagent in that water, like a sodium bicarb or something like that, that will react with the acid gas and take it out of the gas stream. But again, you got to deal with contaminated water. Any questions about emissions? Emissions are pretty fascinating stuff.
How much are those synthetic ones compared to limestone?
Well, the problem is they're not really available in the U.S. yet. There is a company, Lawast, is trying to put together a plant to make them here, but I would guess it's going to be 2 or 3 times.